thank you all for joining. I'm very pleased to see that we had such a huge participation. And yeah, like Stelios said, I will have the chat here. If you have any question, please drop it in. I don't know if I can see the raise of your hand, so just drop in a question, or if it's something fast, unmute yourself and I will reply. Okay, so in this talk, I will give an introduction to high-performance computing. We had a seminar early this year on this topic as well. It's somehow similar, but this is a training. I will focus more on the important aspect of this field. And like I said, please interrupt me at any moment if you have questions. So we will have an overview of the supercomputers available in Europe. We will have an analysis of how this changed during the year. The current technology is mostly focused on CPU and GPUs, on the usage of CPU and GPUs together in this system. So we will focus on this topic, and then I will have a brief introduction of parallel computing. So how it's constructed, what is the setup of a supercomputer? The building block of a supercomputer is a computing node. You can have here on the left an example of a computing node. And there are different components in it. Now we will analyze it, and we will compare this to a desktop computer. So what I can say is that in average, a computing node is 5 times faster, better performing than a standard desktop. So let's compare it to a gaming station, not a laptop. That will be much faster. So if you compare it to a gaming station, it's on average 5 times faster than it. Why? Because, for instance, we can see in this node, we have 3 GPUs. There are probably other 3 below. This node has 6 GPUs. We have 2 CPUs. We have a lot of bunch of RAMs. And all of this is the power you have inside one node. These computers are then made of thousands of these nodes. So this compares, of course, with a desktop where you have 1 GPU, 1 CPU, and some RAM. So usually the memory that you have available here, it's order of hundreds of gigabytes. I suppose the recent nodes have maybe 500 gigabytes of RAM inside, multiple GPUs, and a huge number of cores, around 40, 48, 64. They're inside only one node. What we don't have inside this node? Inside this node, we don't have any hard drive, any memory, and no direct power supply. This is coming from outside. Of course, we don't have any hard drive because the file system, we want it to be centralized. So we don't want each node to have its own memory, its own hard memory. So it's only temporary. And the power system, okay, also there we need for better, how do you say, power consumption, we need, this is also centralized, of course. So this is how a supercomputer looks like. We have many of these nodes inside a rack, suppose 10, 20 of them. And then we have multiple racks put together, connected with cables, network, and this is where the power and the information are going through. Because of course we want this node to be connected to each other, so we want to be able to communicate between one node and the other. In high-performance computing, we don't limit ourselves to use one node, but our application we run on many of these nodes in parallel. Maybe use the full systems in once. So this requires a very good networks that is connecting nodes, one node to many others, in order to have as many bridges possible, in order to avoid switches, so communication going from one point to another in order to reach another node. And they're optimized for bandwidth of data, and they're optimized for performance. In Europe, we have many of these systems. Here I am depicting those that are the tier 0 systems. So we have the current largest supercomputer is a JSC. It's the JUICE booster. This is followed by Marconi 100 at Cineca. And then they follow other systems around Europe. There is the PISDAINT system in Switzerland, SuperMOOC in LRZ, HAWK at LRJS, Julio Curie in France, and this beautiful supercomputer in Barcelona, which is inside a church. You can see the setup here. So these are very big stations that involve a facility constructed around it, because it needs to provide a lot of other inputs. So they require a huge amount of energy. They produce a huge amount of energy, because also, of course, they produce heat, a lot of heat which needs to be dissipated. And these are very big infrastructures, okay? And like Stelios introduced CaSToRC, we have also the largest supercomputer in Cyprus, but this is nothing compared to the other systems. So if you want to learn more about supercomputers, about the latest model, etc., what you need to look at is the top 500. Like said in the name, these reports twice per year which one are the fastest and the largest and the best performing 500 systems in the world. So this is the top 500 is active since 1993. This is the latest release in November 2020. And as you can see here, this is the growth of the supercomputers in the world from 1993 to 2020. The top line is the sum of all the systems. So note here, this is a logarithmic scale. So we are going from 1 gigaflop to 1 exaflop. Where in this scale, the flops, we will focus on this later today, is the number of floating point operation per second. So this is a typical unit measurement of performance in high performance computing, because we use this system for doing mathematical operation. And so we are most interested in how many floating points, so how many multiplication, additions, simple operation these computers can do per second on floating numbers. So not on integer, on floating point numbers. And this is the performance that has grown during the year from, you can see here, this is the number one supercomputer. So it's the one having the most performance out of the 500. And this has grown from 100 gigaflop to 100 to above hundreds of petaflops, and we are very close to what is a mark line in high performance computing, that is the exascale, when we will reach exaflop performance with one supercomputer. So this has grown almost exponentially. Okay, the top one, it's not perfectly linear, because you see, once a newer computer comes out, this might be the top one for many years. But if you look to the sum of this has grown exponentially over the years, almost doubling the performance every year. And we will see in details what are the how these systems are made. What we can observe here is that we had two trends in time. One was followed up to 2014, maybe early 2013, where we had this trend with this exponential growth. And this trend changed due to limits in technology later after this time, and still is growing exponentially, but slower. So instead of having exascale performance earlier, we are reaching it just now. This is why is this? Because the technology of these computers is changing changing continuously, and we reach limits in technology by developing it. So, for instance, something you can see here that is flat out is the frequency a device can have. So a single CPU, its frequency was growing exponentially year by year, and then at some point this couldn't be made faster anymore due to limits in the physics that this system have. Something that is growing exponentially since ever is the number of transistors contained in the systems. These, we can pack them more and more inside the systems. And to compensate those limits in technology that cannot be overcome, like the frequency, companies started to develop, to exploit other ways to increase performance. And for instance, you can see that after 2005, we started to have the first CPUs that use multiple cores, so the name threads, and you all know that your laptop doesn't have only one core, but whatever CPU you have, you might have 4, 8 threads that are running together. And these has started to grow since then, and we are having nowadays CPUs with hundreds of cores inside it. So let's have a better look to what are the top systems in the world. So here, this was data in November 2020. The top system was Fugaku in Japan. This was a system made only of CPUs, in this case are ARM CPUs, which had 48 cores per node. The second system is Summit in USA. Here we see an hybrid system instead, where we have IBM CPUs together with NVIDIA GPUs, Voltas. And you can see the difference. Okay, here there is a bigger difference in performance. Let's take another system that is made only of CPUs, like somewhere in China. You can see that this system has a maximum performance of 93 petaflops. It compares with the same performance the Sierra systems in the USA, where though the number of cores is 10 times less. Why the number of cores here is 10 times less? Because this one is an hybrid system that has together with CPUs, GPUs. And usually what happens in this hybrid system is that the CPU is not the top category. You see here, this one single CPU has 260 cores, this one has only 22. But because what one wants to exploit in a hybrid system is mostly the GPUs, this is the one providing the most performance out of it. So this trend of having hybrid system is quite common nowadays. And we have, for instance, the top system in Europe are all made of CPUs plus GPUs, like you can see here. And the performance we have in Europe is, the top performance is 44 petaflops. That compares well, it's 7th in worldwide. So yes, so all these systems have NVIDIA GPUs. This is a very, something very important for doing, something very important to know for doing high performance computing nowadays. And yes, if so the picture we had until now is that the largest market share in high performance computer is taken by Intel and NVIDIA. So since 2010, we started to have the first system with first hybrid systems. This has grown, the number of this hybrid system has grown very fast in the top 500. So we have 150 systems nowadays that are hybrid. And here on the other end, you can see that Intel, most of the systems are equipped with Intel CPUs. So yeah, now let's have a look to the picture in how this is going to change in the next years. So Stelios introduced the EuroHPC project, which is this national competence is part of. In the EuroHPC joint undertaking has planned to bring in Europe, is the entity that will found the next supercomputers in Europe. So up to now, we have it has found 5 petaflop systems are the one in light red in the map, 3 pre-exascale machines that are going to be in Spain, Italy, and Finland. And we will have in 2023 or later, probably the first exascale systems that are going to be announced, that for which a call will be opened soon by EuroHPC and will be announced later in maybe in a couple of years. Okay, these are the specifics of these 3 next per exascale systems in Europe. We will have LUMI, which is expected to be, which is they're constructing now. It was announced to be active in 2021. We will see if now this is going to happen, but between this year and the next, this will be operative. And it will have a performance of 500 petaflops. This is a huge number if we compare it to what is the largest system in Europe, that is 44 petaflops nowadays. So this is 10 times bigger than the JUICE booster. This system is equipped with will be equipped with the AMD CPUs and the AMD GPUs. So this is one of the important aspects that is going to change in the new pre-exascale and exascale systems, where we will have we will not have only NVIDIA GPUs, but also AMD GPUs inside these systems. This is quite critical for us, and we will talk about it later, because each hardware, each architecture requires a dedicated development of the software. So a question came in, and is what are the cost of these HPC systems? These projects are of the order of 10 between 10 and hundreds of millions. I don't know the correctly for LUMI. I think was around 200 millions, but maybe someone else can comment on it. But yes, are big facilities that all of you can access by writing, by submitting proposals for projects, and are available to the community, to the scientific community, for performing research in HPC.
So maybe a comment to the EuroHPC machines. So 200 millions comes from EuroHPC, and the other half comes from the countries which are in the consortium of this machine. So these 4 machines are around 400 million.
Correct. Thank you, Jakob.
Each.
Yeah, I forgot to mention. I had in mind the 200 millions of LUMI, but yes, it will be around 400 millions. But it's not just a system; it's the full facility. They will build up. In the case of LUMI, they will construct a complete infrastructure, a new building for it, for hosting it. So it's not the price only of the technology, but of putting it in.
No, sorry, maybe it's 100 million. So I'm also confused. Yeah, I think it's 100 million from EuroHPC, and the rest is coming from participating countries. So it can be up to 300, 400 million.
Okay. So yes, so these are the pre-exascale system founded by EuroHPC. Pre-exascale because we are very close to exascale, but not yet. The first exascale system, we will see them in USA. And these are the 3 next supercomputers that will come out in the USA, and are El Capitan, Frontier, and Aurora, all of them above or at the exascale performance. And you see again, no NVIDIA GPUs anymore. AMD GPUs, both of them, and Intel GPUs here. So all the hybrid systems, but not NVIDIA anymore. So there is a new player in the supercomputing system, which is NVIDIA, which is AMD. Sorry. Okay. Yes. So, what are the specifics of these hardware that I'm talking about? Most of you might know that what a GPU is. Okay, it's something you have in your computer and it's very good for graphic. That's what you might have in mind. I don't know if you ever used it for doing other kind of calculation on it. But yes, the GPU is a very powerful piece of hardware, and which is usually combined with a CPU. So the CPU is a must in a computer. This is something all computers have. So how these are made inside? These the CPU. These are computing logic units, and you see that, for instance, CPU has few of them. Let's say 4 cores. These are the cores that we were talking about. Then the CPU is something then cache. The cache is a kind of memory that is directly inside the CPU. So in a computer, you have 3 kinds of memories. You have a temporary memory, which is the RAM. You have instead an indefinite memory, which is the hard drive, where the data will not be lost. The RAM instead is a temporary memory where the data are loaded from the hard drive, but when the computer is switched off, is completely erased. And then you have a memory inside a CPU that is then cache, which is where the data are loaded from the RAM and is meant for very fast data bandwidth between this memory and the computing units. So the CPU has a very big memory inside, very big cache, which is usually named L3. So it has usually 3 levels of cache: L3, L2, L1. The largest is L3, and it's used by all the cores. Then inside the cores, there are smaller ones that are named L2, L1. This is level 1, level 2. And so it has a very big cache. It has a very big control unit, which can where that manage the data access and the operations that the CPUs perform. And all of these, yes, it's this makes a CPU. On the other end, we have the GPU. So the GPU, what does it have? It has a dedicated RAM, which is named video RAM. And you can see it here are these chips here, this piece of hardware here. So it has its dedicated RAM where the data are loaded from the DRAM of the system. So the CPU itself is the one responsible of saying of sending data from the DRAM to the VRAM. It requires a VRAM because for fast data access. So the data, this is a large memory. It's usually of the order of gigabytes. So this is where the data is loaded. Then it has thousands of logic units, smaller one, but thousands of them, and smaller cache and smaller control units. So the purpose of the GPU is to perform high throughput computations where the same operation are performed on all the data. So it's very good for graphics because graphics is just a matter of managing the screen and of doing operation of the pixels, for instance, or of recreating something, a scene. And it's something that requires to do the same operation on all the data simultaneously. So it is optimized for high throughput. On the other hand, instead, the CPU is optimized for unordered data access. So it's optimal for doing random operation that they're not connected to each other. So for it's optimized for doing calculation that are that has low latency, but it's not meant for high throughput. So these are the two kind of hardware that we have in supercomputers. And yes, for the kind of calculation we do nowadays, GPUs play a very important role, because we are doing a lot of big data, and the GPUs help us to do this calculation much faster. So everything you do from machine learning to, I don't know, biology and whatever, it gets, it will have a huge benefits from exploiting a GPU. So yeah, please interrupt me if there are any questions. By the way, I forget to, there are people in the waiting room sometimes, and I forget to join them. So yeah, why the architecture is important? So why do we focus on the on this kind of architecture? Because when we do HPC, it's very important to know what with the specific of the machine we are going to deal with, and what we have to do is optimize our software for it. So we don't develop software just for the, we don't develop a normal software that then will be run on a simple machine like a laptop, etc. So it doesn't have to be optimized, but we are always interested in optimizing our code. So when we optimize a code, we need to know the specification. We need to know what is the memory bandwidth of the system. So we need to have the best deal between how much data we can load and how much calculation we can do with it. Then we need to know for the number of cores, how big is the system, and we need to know if it is optimized for some kind of operation, etc. So what these are all specifications that one needs to know before accessing a system, and then it needs to try to optimize the code for it. So I think all of you wrote some code in their life, and usually when you write when you write some piece of software, unless you use an interpreted language like R or Python, but if you write it in C, what you have to deal with is a compiler, which will produce the compiled code, so machine code that will be then executed by the hardware. So by the way, also, if you use interpreted languages like R or Python, under the hood, everything that is going to the computation has been compiled. It's just that what you execute, it will be executed on time interpreted. So you have a programming language like C, that is a very common programming language in high performance computing, or like Fortran, which was used back in the days, C++. These are all the widely used programming languages. Then you have a compiler that will translate your text in a code that will be then executed in the hardware. And usually it's the compiler doing the job for you. So the compiler knows what is the hardware available on the machine. So with what kind of instruction set it needs to deal with, because it needs to try to, each machine has its own instruction set. So for instance, if you take a software that has been compiled on my laptop and you try to execute it on another laptop, this might not work. Because if you don't have the same CPU, etc., it might have, the compiler might have decoded in the set of instructions some kind of operations that your piece of hardware doesn't have and cannot execute them. So the compiler knows what is your machine, and we compile the code for it. And usually knows if it is a very advanced CPU, it knows how to optimize code for it as well. But sometimes we need to help it. So sometimes we need to put inside our software some instructions to help our compiler to do a better job. And this, you will see it mostly on Wednesday when Jaco will talk about OpenMP. For instance, OpenMP helps you to give some inside the code some simple instruction that will say to the compiler what to do, how to optimize the code. But this sometimes it's not enough. So sometimes when you have something like a GPU, it's not enough to have what the compiler does, but you need to develop your software in a completely different way, because you want to run code on a GPU. So the GPU programming languages are, each GPU have a specific programming language. So for NVIDIA GPUs, there is CUDA. For AMD GPUs, there is HIP. And these programming languages add a set of instructions to the base programming language. So are not completely new programming languages based on C or C++, but they extend this programming language with a set of instructions that are specific for the hardware you're going to run on. Because what you want to do with the GPU, for instance, we had it before, you want to move, to give instructions and move data from the RAM to the GPU RAM, or you want to say what operation needs to run on the GPU and how to run them. And you have thousands of cores, and so you want to say also how to distribute between these cores your tasks. So when you are dealing with accelerators, they are not anymore a simple CPU where the compiler can do a very good job, but you need to instruct to rewrite your software in a different way. And this is the big deal in HPC, because nowadays that the technology is changing, one needs most probably to rewrite his own code again and again in order to optimize it for the newer system. So these are it's the most time-consuming component of HPC. There are ways to avoid to do all of these, and there are this kind of all-in-one solutions, so like OpenCL and OpenAPI of Intel. These are frameworks that hide to the user what kind of hardware you're going to use. So it's abstracting the hardware operation and then translating them for you for each hardware. They usually get a good performance, but yeah, depends on how advanced you are. Sometimes there is no way to get the optimal performance if you don't write your own code, your own kernels. Yes. So let's talk a bit now how we use these supercomputers. So there are different ways to use sorry, there is someone that cannot hear me. Everybody else can hear me. So I think
we can, yes.
Yeah,
so,
yeah. Okay.
Diriago, if you can't hear, then just log in again.
Maybe we write in the chat. Okay. So what I was saying, yes. Now let's have a look on how we use this supercomputer. So here I'm going to explain 4 that I think are all the kind of computing paradigms that we use in high-performance computing. These are namely task parallelism, distributed data, pipeline parallelism, and modular computing. So what you want to do, like we said at the beginning, we are trying to optimize our code in order to run on a very large system, so many nodes. And this requires to think well about what is your workflow, the workflow of your code, and now you can parallelize it. So parallelizing is the keyword in high-performance, is one of the keywords in high-performance computing, which means you need to run your code in parallel. So you need to exploit all the nodes together and do the task, the operation. Okay. So one very trivial way that is, for instance, is what your operating system is using is task parallelism, multitasking. So you have different kind of tasks you need to execute. They may take a different time, and just you run one by one. You run them separately. You exploit the cores. This is a trivial way, but it's if in most of your problems you run out of tasks very easily. So what you are most interested in is to distributing the data. So okay, distributing data in a trivial way, it's also very easy. You have, or depends on the problem usually, but most of the time it's very easy. So you have a big amount of data that you need to process. And instead of processing only one core, you split your data in different chunks, and these chunks are given to the different processes, and they are processed in parallel. Okay, this might not be one of the this might be trivial seen in this way, but it's not one of the trivial tasks, because there might be operation that when you're distributing the data on your supercomputer, you have the different nodes, and when you put some data on one of these nodes, this data is not visible by another node unless you communicate it, and this costs a lot. So it's most of the time it's much cheaper to recompute something again than communicate it from one node to another. So you need to think well about your problem. So if it's a trivial problem like task parallelism, that you have different tasks that can run in parallel, then also here it's trivial to parallelize via data. But sometimes the same data is needed in other places, so you need to find a way on how to distribute your data between different nodes in order to don't require too many communications. So communication are fine, but in a limited number. And most you need to do is computations. Okay, so these we will have later today some examples of distributed data. Another way that now this is a more advanced way, that is named pipeline parallelism. So suppose you have some dependencies between one task and the other. So before we came task parallelism, we could just run them in parallel, because we supposed task 2 does not depend on the result of task 1. Clear. So if it does not depend, I can just run them in parallel, I just execute them. But if you suppose the task 2 depends on the task 1, then this cannot be executed unless you have the results of task 1. So with the name pipeline parallelism is somehow the process that you have in industry when you are producing a car. The car is made of various pieces, but you don't construct, you don't build each pieces in a serial way and then assemble the car. But what you do is to have a pipeline mechanism where there are different pipelines building different pieces. And when one piece is ready, I give it to the next pipeline to compute, to process it. And then when these results is ready, I give it to another pipeline, etc. So if you have operations that require this kind of dependencies, this is the kind of parallelism you're going to use, where the one core is dedicated to a kind of task, or to produce to analyze a set of data. So these don't have to be tasks, can be also data, to process a set of data. And then when task 2 requires a result, we will send it to the other and keep going in this way. So we are accelerating our process in by this fashion. Another kind of computing paradigm that it's the topic nowadays is modular computing, because indeed in these systems that we saw before, we have, as I explained, different kind of hardware. We have the CPU and the GPU, which have different kind of specifications and properties, and each of them is faster than another on doing some operations. So for instance, here I'm considering some tasks run on both CPU and GPU. So we suppose that, for instance, the GPU is faster on doing task 1, maybe much faster, let's say, than the CPU. But on the other, the CPU is faster than the GPU on doing task 2. Task 3 takes the same time on both, and here the GPU is faster on doing task 4. So what you want to do in your problem is to understand which parts of your code optimally perform on which part of hardware, and you might want to distribute them unevenly between the hardwares in order to optimize the computational time. So for instance, here I'm putting the tasks that are faster to be run on the GPU and the GPU, and the others on the CPU. Okay, so this is with the name modular computing is when we consider the different modules for performing different kind of tasks. And this is what one should do for fully exploiting the systems that are available. Though most of the time, for instance, when you have a GPU machine, it's enough to just run on the GPU. So usually the CPU, this is the idea also of what I mentioned before. Usually a GPU is accompanied by a weaker CPU because the system managers thought that anyway the users will only use this GPU. So it's not mandatory to exploit always both CPU and GPUs if you have a GPU. The important is that you use the GPU because the GPU is the big guy inside the node. So a couple of questions came. Ronnie asked, what is the amount of time deciding the optimization process? Then Christos asked how we deal with dependent tasks in modular computing. And Ronnie asked again, how can we simulate any task to predict the time spent? Okay, these are good questions. So, okay, about how much time, what is the amount of time deciding optimizing a process? So yes, now I'm introducing the topic from a theoretical point of view. So there are many ways to optimize your code, but of course, all of this requires a lot of human times, and most of the time it might not pay back to spend. I mean, also the human time is very precious, so you may not have time to do everything you wanted to do. Though there are some, with experience, you learn some very important steps that that gives you with a short amount, with fewer energies, a lot of benefits on these systems. And of course, experience is what everyone requires to be able to run efficiently on a Hpc system. So you need to try out several things at the beginning until then you have enough experience to judge well what is the optimal way to execute a code. Now, the optimization process, there are tools that helps you also to optimize the code. There are things that are named profilers. So you can run, you can take your code. There are pieces of software that are named profiles. Usually are coming in, are provided by the system administration. And these help you to profile the software and tell you which one are the weak part of your code and what are also the parts of code that you may want to change in order to improve your performance. This is something we will not cover in this training, but will be most probably in intermediate training. Let me try to reply to other questions. So how do we deal with dependent tasks in modular computing? So in modular computing, usually of course, we are talking about modular computing when different hardware is inside the same node. So it's faster inside the same node to send data between the pieces of hardware. So it's faster to send data between the CPU to the GPU, faster than sending the data from a node to another. So that is the slowest thing you can do in a HPC facility. But the slowest is accessing data from the file system. That is the very slow. Then sending data between one node and another, it's slower. And what is faster is to send the data from device to host. This is fast, though you want to avoid as much as possible the idle time. So you want always to have tasks to be executed by your device or by your CPU. So you can send data. Suppose now task 3 requires data from task 1. The communication already started maybe from this point here. So when we started to have some data processed, we started to offload it to the CPU. Or the opposite, the task 4 requires data from task 2. When we start to process some data, we start the upload to the GPU. in order to have in memory, in the device memory, the data to be processed by task4 directly. Of course, depends everything on your case. So when you have your problem, we will have later on, I think next or in 2 times, we will have an hackathon where you will come directly with your problems and we can discuss how to optimize your specific problem. Or later today, you can also ask me questions about your specific problem, how I will parallelize it. Yes. Let me read Rones again. So in modular computing, it is the human who decides using CPU or GPU in several tasks. Of course, it's always, okay, everything depends on, there are software or way to program that help you, that do some of the job for you. Though it's very difficult to build a very smart tool that can help everybody. So they try to do this, like I mentioned before, the one API, OpenCL and one API. So these tools will help you to write only one piece of code that can run on any device you have inside your node or on the futures node, on the CPU, GPU. But then you need to trust it that is doing the best job for you. And that's the difficult part, because you are the one that knows as best what your problem requires. So with experience, you may want to try one day to, instead of basing your software development on one of these generic tools, to compile your own kernel and try to speed it up. Of course, what you need to focus always is on the most time-consuming kernel. So when you run on your application, these are also where profilers are useful. You may see that some tasks, even if you do them thousands of times, they may take each time 1 millisecond. And if these take 1% of the full time, okay, you may find a way to optimize them, but it's not the part that you want to focus on. What you always want to focus on is on the part where analyzing the performance is the part that is taking most of the time, but you could get most out of it. So those are the kernels that you want to optimize. So that is where you want to spend your human time for improving your code. But all of these, yes, comes with experience and by trying out things on the machine. Okay, so how to use these? How do we use HPC? Let me also check the time. Okay. So how do we use these HPC systems? First of all, we need a scientific problem. The scientific problem must have a numerical approach. So you need to know how to use computational resources for computing your problem. Then it must be also computationally intensive, because if something can run on your laptop, also efficiently. So if you can run efficiently and in order of minutes, you can have on your laptop everything you want. Of course, you don't need HPC resources. So HPC resources are for something that requires a huge amount of resources that have to process a huge amount of data that maybe cannot be analyzed on your laptop. So in our case, when we do our calculation, we produce terabytes of data per second. So these are huge amount of data that your laptop cannot handle. And if they are computation intensive, so suppose it does not have to process a lot of data or a big task, but maybe on your laptop takes 1 day to do one calculation, then there you may consider to start using HPC resources. So it needs to be computation intensive and needs to be parallelizable. So most of the things you can find a way to parallelize them. There are some problems that you cannot parallelize them at all, and then there you just need one better device, but it's hard to exploit this system if you cannot parallelize the software. When we talk parallelizable, means that your code can scale. So if running on one node, if the time it takes running on one node, when you go to 2 nodes, you take half time. then that means that your problem is parallelizable. So if your code is scaling as much as you increase resources, as less time it takes. Of course, there is always a trend where, okay, it's increasing linearly correct with the node, and then at some point it flats out. That's fine. Though when you are sailing, when you are applying for resources, you need to show that your code is parallelizable. So you need to show that going from one node to two, you are getting a speed up. So yes, then you need to develop a software. There are, depending on your problem, usually, unless it's a very specific problem, there are already software available for HPC that you can use. So you can easily look online. If you use the keyword HPC parallel computing, and then you you look for your field, you will find softwares that are written to be used on HPC systems. And so you need, or you can write your code, you can extend this software in order to solve your specific task. But yes, usually if you are not an expert, it's better to start from some software already written and write your own. Then you need access to a supercomputer. So this access to a supercomputer, you can get it in different ways. We will see probably tomorrow. Okay, tomorrow all of you will have access to our local cluster. Usually all the supercomputing system can give you preparatory access to it. Preparatory access means that you get a small amount of resources where though you can, during this time, you can compile your code, try to run it on the system and prove that it can be parallelizable and it's efficient on the system. Because then after that, to get the real amount of time that is the significant, what you need for running your scientific program, is to write a proposal. These proposals usually are written in a competitive manner, so they are evaluated in a competitive manner, which means they open a call, 50 different groups apply with a proposal, then these are given to a committee to judge them, they judge the technical part, the scientific part, and then you might be awarded of the time you've asked for. So in these proposals, you need to include the software test, benchmarking, and show that you are ready to use the system. Because these are huge systems that everybody can access, that does academic research, but though are very precious resources. And yes, and then, of course, when you get access to the resources, you can start production of your results. You produce data. You do all your scientific programming. You will produce publications out of it. Okay. This is other kind of activities you may do during this time is also some algorithmic research. So it's always useful to think about better ways to write your to translate your scientific problem in a computational task. So here we are talking about algorithms. So you need to think what is the best algorithm and the most suitable algorithm for the architecture you're using in order to produce the data you need. You may consider numerical improvements, extra software development. So once you have access to the system, you can always look forward to develop more software. You can always have a look to the new papers coming out and what people are working on. And you may consider to use machine learning, which is a very hot topic recently for improving your scientific program. And about this, Chris will talk next. Chris has asked, can we use a ready-to-use simulation software in HPC like Cosmos, Fluent, etc.? Of course, as far as it's a software for HPC, so which means it's parallel and you can run it on the system and it's optimized, it's perfect to use the software. Actually, sometimes it's even better if you, because if you don't have, in order to gain access to the system, it's not important to have your own software. The important is to have a significant scientific program that will advance our knowledge. So you need to show that you are doing something that is cutting edge research. And on the other hand, you need to show that you run efficiently the system, but it doesn't mean that you need to run with your own code. The important is that you use a software that is suitable for what you're doing and is it's optimized for it. So you need, and these you show it by running benchmark and scaling of your code. So this is what you usually do. Okay. So early this year, some of you may have taken part to a questionnaire where we ask what Hpc research has been carried out in Cyprus. And this is just to give you an idea of the variety of the fields we are dealing with, also us as a National Competence Center to help you with. So what we are trying to do in our training is not to focus on how to solve a specific problem, but to provide you generic information that then you can use for having access to Hpc resources for solving your problems. So also today was very nice to hear what all of you are doing research on, and you clearly show that we have a very large variety of problems that we are trying to tackle, and we are here to help you to do so. And how do we help you to do so? We have our system that Stelio mentioned about, that is Cyclone. This is our current active system. Previously we had Cythera. On this system, it's not a big system, as I mentioned at the beginning. It's not one of these huge exascale systems that are available in Europe, but it's a good system that has the top technology. So it has one of the latest model of NVIDIA GPUs. It has one of the latest model of Intel CPU. So it's top technology system. It's just not big. It has few nodes. It has 16 GPUs node and 32 CPU only node. But you see the 16 GPUs node are equipped with 4 NVIDIA V100, which are the previous latest model of NVIDIA, was A100. But it's a system that is compatible with what you have available in the large exascale, in the large tier 0 systems in Europe. And it's the perfect for all of you that are attending now the beginner training, so you don't have yet an experience with Hpc, is the perfect system to get experience with for then preparing your software and your scientific program to then access the large systems in Europe. So this is what we want to do with our training, to help you. We provide you access to the system. You can apply to it for preparatory access and for production runs. So the preparatory access, it's a very simple form that you can fill in, and it requires 1 page of detail of work, and you can do you fill in the details of your calculations, and you will get a small amount of resources that then it's very useful for you to start running your program on the system. So with very small of work, you can get access to our supercomputer. And as next, twice per year, we have a preparatory access call. The one just closed. The next one will be somehow in 6 months. That is a call where you can submit a proposal. This requires a bit more of work. It's around 10 pages where you need to fill up your scientific program and all your technical details, provide a scaling plot, etc. And but when you get when you get production access, then you can start to run your problems. And the next step, of course, is to apply to one of the big calls in Europe. And yeah, so we have this is the system you're going to use tomorrow. Tomorrow you will get access to it. We have other small prototype systems that we are using in our research, and we are here for helping you with it. So I think we have 10 minutes more if you have any questions. Otherwise, I will give the words to Christos. Please unmute your microphone now if you want to ask something.
Hello, this is Nicolas Patsalidis.
Hello.
I have a question about a more general question. What is the power needed for a facility, maybe per node?
Okay, the power, you mean the power supplied energy,
Yeah.
the energy consumption. You can see it here in this table. So this is the power in megawatt hour.
Okay, thank you.
So yeah, they need, this is the power they consume at peak performance, and they need a huge amount of power, and they produce a huge amount of energy, like we said. Somehow this energy is like the picture of SuperMOOC. Something they did first year at LRZ Munich with SuperMOOC is, for instance, to use the heat produced by the supercomputer to then bring, how do you say, a centralized heat system for the town. So this is in Munich, and the hot water that the supercomputer will produce will then bring warm during winter in the, I don't know in what size, but it's then used for instance in this way. So, but yes, they use a huge amount of power, especially the GPUs, and this is why are also very precious resources, because when you are running on the GPUs, nobody will credit you about how much it will cost your program. So you don't need to worry about that, but you need always to use these, they are worried that you use these resources in an efficient way, because when you get, I don't know, millions of node hours on one of these systems, this might translate on thousands of euro of energy consumption, which is not something, I mean, this is for research, so it's a all fund kind of funding coming from Europe.
Yeah, thank you. It's mostly for cooling, right?
No, the power, the power it's used mostly for by the devices. I mean, for producing data.
Thank you.
All the power is used by the devices. Then all this power that is used is translated in heat, then needs to be cooled. And how they get cooled down, yes, depends. Sometimes it's also about quite critical, but yeah, for instance, most of them, they have AC systems that with clean air, they cool down the system because you don't want to have dust, etc., going around. So of course they are water cooled mostly, but then the environment itself needs to be cooled. So all the cabinet usually acts like a cooler, a dissipator.
Okay, thanks.
Sorry, Simone. Soderi, you have a question?
Yeah, thank you. Okay, from what we know right now, the CUDA performs better. Okay, but you have shown us that the new systems have chosen AMD GPUs. So, do you expect that to get any improvements in the OpenCL?
Okay. Yeah, I mean, okay, when you say CUDA performs better, I think you mean NVIDIA GPUs perform better.
Yes, NVIDIA GPUs, yes.
Than AMD GPUs. So because CUDA is the programming language. Of course, let me go to the table here. Of course, so far, NVIDIA has been the best at producing GPUs, like Intel has been the best so far at producing CPUs. But I don't know if you follow some of these, also there are these YouTube channels like Linux Tech Tips. He really gives always, it provides always very nice videos on the latest technology. And there you see that AMD recently has been able to really come over Intel and produce devices that are top market, also in matter of performance. So some days ago, if one was asking, do you want an AMD CPU or an Intel CPU for your laptop, you would say, of course, Intel, because you knew that AMD wasn't performing best. It wasn't needed, maybe so widely support optimized by your hardware, by your software. But yes, the latest model of AMD are equivalent to Intel at level of performance. And we don't know yet about AMD Instinct. So the latest AMD GPU, it's not available yet to the market. So you don't have equivalent to test. But there has been a reason why this has been chosen, and so they won. They come out with a call for how do you say, procurement. They come out with a procurement for these machines, and the provider of this machine passed all the tests and of course showed that AMD GPUs, the next generation of the GPUs are better than NVIDIA. So this has been able to win the procurement. Okay, so we don't know yet, but of course we expect these GPUs to perform as much as NVIDIA and to be probably cheaper because of the market. But yes. Panayoti is asking, do you think the future is ARM? We repair to that. Okay, let's repair to that. ARM, you know, it's this kind of CPU, lightweight CPU that we have also on our mobile systems, etc. And the idea of ARM is to have a very one of the most the important specification of ARM is to have a low consumption. So to be able to I mean, the reason why you have an ARM CPU in here instead of an Intel is just for battery, for energy consumption, that are able to produce a very efficient in processing data at a low cost of energy. This is one of the reasons why ARM systems have been adopted by supercomputing facility. So Fugaku here is made of ARM. So the largest supercomputer in the world is made of ARM. And the reason why it's made of ARM is because, of course, the ecological impact of this system is also very important. And one is to prove that you can get a very high performance with a cheap cost in with a cheaper cost in power consumption. So you see here that there are 30 megawatt and it's somehow equivalent. So it is a factor of 3 bigger and it's it has the same consumption. And though you see here, for instance, this Sunway is consumes for 100, let's round it up to 100 petaflops, consumes 15 megawatt, which is half, but this is 4 times better. So the main feature of ARM is this one, to have to be optimized for data processing versus energy consumption. This is one of the reasons which has been chosen. It just yeah, they have a lower performance compared per core, and to use them in high performance computer, especially for processing numerical data, it's difficult. One, it requires to optimize the software in a different way. In this case, this is again what I mentioned before. Going from an Intel to AMD CPU, it's 1-to-1, so you don't lose performance going from Intel to AMD CPUs. But going from Intel to ARM, you may need to reconsider to rewrite parts of your software because to rethink how you optimize your kernel. So it requires to optimize them again. Other question came out. For some interested in entering the HPC field, what are the best must-have tools to learn? Panayot asked this. There are a lot. Depends on mostly on your kind of application. So, as I said, the first step is to investigate what software is available for HPC for your kind of scientific problem, and then also depends on what system you are going to deal with. So, if you are the must nowadays is to run on GPUs, so that's one of the focus you need to have. This is really on the problem. Panayotis asked, I think it's also simplified pipeline that is probably more scalable. This is about ARM.
Yes, Simone, I think, well, my intuition is that because ARM processors are RISC, so they are reduced instruction set command. So basically have a simpler pipeline, so it's easier to optimize. So compilers are also going to be probably better for.
I know that just the risk is not always an advantage in our case because we in high performance computing what we want to process. I mean the how do you say, what we look at are the flops, or the floating point operation we can do per second. And the kind of CPUs, the Intel and AMD CPUs that are given on these systems are very optimized for numerical operation, which ARM system weren't previously. Now the new generation are going to have this kind of, for instance, the multiple data, single instruction, multiple data operations, and also combined operation. I can mention maybe, for instance, something that Intel GPUs, an example is that they do in one clock an operation like AX plus B. So they can do they do hybrid operations where you combine for processing your data. And these are all put in to optimize performance. Usually ARM is a more, having a restricted instruction set is not covering all the instruction set that Intel or AMD would have. So the best performance is given by an Intel or AMD CPU at taken one-to-one. But if you're going to analyze performance per power consumption, of course, ARM is winning. But if you go to look at the time, it's the other is the Intel is performing better. And about time, I'm also running out of time.
Simone, hold on. How much more do you have?
No, I finished. There was a question more, if anyone.
Okay. If I can say about the questions, so this last question, if you want to answer, will also be available during lunch break. So some of the trainers will be online. We won't be recording. So if you want to ask any questions, general questions for a general chat and more relaxed and so on, do so, okay? We can take some time there.
But Stelios, there is a way to don't have the waiting room to the host. I mean, or having someone else as a host, because I had another person waiting.
I can handle the waiting room.
Yeah, okay. Yeah, because, perfect, thank you. So, okay, so this was it. We will talk, we will talk later again in the afternoon session. So now Christo is following, then Stelios will talk again, then I will be for 2 hours to introducing you on parallel programming. So thank you very much for now for your attention. Talk to you later. Bye.
Okay, Simone, thank you very much.